right. So welcome to the second lecture of the second day. So lecture number 6 in the Sheaf tutorial. So we're going to talk now about computing topological features. So taking the homological algebra that we've built in the previous lecture and applying it to topological spaces, computing topological invariance using the machinery of homology. This will actually make very concrete how we do computations of topological invariance. Okay, so where are we in the discussion? So we are now in lecture 6, so addressing homology in great detail. We mentioned the definition of homology at the end of the last lecture. Now we're going to build out that homology now. Build it out and talk about it from the point of view of topology. So what do we want to do? We want to identify robust and interesting features of topological spaces, i.e. those features that are robust to large perturbations. Precisely convert our spaces into linear algebra. And how do we do that? We're going to turn them into chain complexes. And the other thing we're going to do is then we'll analyze that space up close topologically using local homology, which is something that is computationally very effective and computationally easier than addressing the whole space globally. This is an idea that has been around in the applied topology community for a while, and I think it hasn't gotten enough exposure. So I'd like to give it the exposure that it deserves and show you how it's quite useful. Okay. So where we ended off last time was we were talking about this chain complex, and I had mentioned the Euler characteristic, which is this alternating sum of dimensions of a chain complex. So this thing is a bunch of linear maps where if I take the pair of linear maps that are adjacent to each other, so take any pair of adjacent linear maps and compose them one after the other, I get 0. So the kernel of this map contains the image of the map before it. That's a chain complex. And I'm going to define the Euler characteristic to be the alternating sum of the dimensions of the vector spaces in this chain complex. And I made the point that it turns out that this is also the alternating sum of dimensions of the homology spaces, which are the kernel modulo the image, telling you how far away is this sequence from being exact. Of course, what that means is that if I have an exact sequence, then the Euler characteristic of that sequence is 0. It's kind of a useful feature. The fact that the Euler characteristic is 0 does not imply that you have a chain complex, that you have an exact sequence, though. So it's only a one-way implication. Now, you've probably heard of the Euler characteristic in another context, that of combinatorial topology. Something like, I don't know, vertices minus edges plus faces, something like that. Well, it really generalizes counting. So here's a space, an abstract simplicial complex with 3 vertices, no higher dimensional simplices. And the Euler characteristic of that is the number of vertices, which is 3. It generalizes counting. The reason for the alternating sum is that if I add an edge, well, then how many objects do I have here? I have 2. Here I had 3 objects, 3 connected components. Here I've got 2. So if I look at that and I say, well, how did I get that? Well, I added up the number of vertices, subtracted the number of edges. There's 1 edge, so I get 2. Of course, it works if I add another edge. Now I've got only 1 connecting component. And it works if I add 1 more. I get 0 connect. Wait. There are not 0 connecting components here. There's something wrong. Well, what I should probably do is put in a face, add in a 2-dimensional face. So I have vertices minus edges plus faces. And now it's back to 1, as it should be. This is the number of connecting components. And I can imagine doing this all the way up the chain for a simplicial complex. And in some sense, if I've got a flag complex, this will count connected components. Cool. Well, then I get this. Well, it is a number. It is an invariant. It is a topological invariant, in fact, which is sort of interesting that if I take not just this guy, but let's try, instead of having a triangle that's empty, I have a square that's empty. Well, how many vertices? 4. How many edges? 4. Still 0. This is a topological invariant. So any circle thing is going to have Euler characteristic 0. It's not really counting in the same way that you thought. It's counting something else. And so this particular object is kind of neat. It actually goes very deep. It goes all the way down to the Gauss-Bonnet theorem, which is one of the deepest theorems in differential geometry. So it links up all sorts of neat things. So for instance, if I have a sphere, what's the Euler characteristic of a sphere? It's 1. And you can do other sorts of interesting computations. All right, cool. Now, actually, the Euler characteristic of a sphere is not 1, it's 0. Anyway. You know, this is something that involves arithmetic, and I'm not going to do arithmetic right now. Anyway, point of the matter is, it's not the least bit obvious, though, that this thing is a topological invariant. I mean, you really would have to work very hard to figure out that this thing is a topological invariant. It's very easy to find this thing, but it's hard to compute it to show that it's a topological invariant. The right way to do this is to show that actually it's homology, and that homology is a topological invariant. And even that is not easy. But this is the path that we'll take. So what we're going to do is we'd like to say, well, this is the alternating sum of the number of k simplices. That's the Euler characteristic I just defined for you. So 0-dimensional simplices, that -1 to the 0 is 1. And so this would say the number of 0 faces, i.e. the number of vertices, minus the number of edges, plus the number of 2 faces, etc. That is an Euler characteristic. And I'd like to find a chain complex whose dimension v's match up with the number of k simplices. So what I should do is build a vector space whose dimension is the number of k simplices. Then that would make this linkage here. This linkage would then say that this property of this abstract simplicial complex is a homological property. That if I want to find the properties of this topological space, I can use homology to compute them. OK, so let's walk through this. Turns out this is a kind of categorification to turn this from arithmetic into vector spaces. OK. All right, so let's go ahead and do that. So first of all, what I need to do is I need to build out my simplicial complex as a chain complex. So one thing that I want to do in how I build this out is I do want to keep track of signs, because I want to worry about alternating sums and other such things. So this is a place where we need to actually pay attention to orientation. The right way to do that in a simplicial complex is to look at not just the simplices being sets of vertices, but rather to look at them as ordered sets of vertices. This means that if instead of working with graphs, I'm working with directed graphs. And instead of working with something that's, say, a 2-simplex, it's got a particular ordering on it that says, I go from this vertex to this vertex to that vertex. And once I start making those kind of choices, you realize that I may choose an ordering on each of these simplices that is not self-consistent in some fashion. That, for instance, if I have the following simplicial complex, this filled-in triangle, 1, 2, 3. If I have this simplicial complex, and let me orient it, 1, 2, 3, and I have another, so they're coming in the order, 1, 2, 3, in the order first, second, third, that I may, in fact, have chosen an orientation on some of the faces that is not quite self-consistent. And then, of course, then I've got the singletons. And I'm not even going to bother writing the empty set, because it's in there too. But I will close off my brackets. OK, so if I take a look at this simplicial complex, and I look at the ordering, now I'm going to write down the orderings on these things. First 1, then 2, first 1, then 2, and 3. I get some ordering like that on this simplex. I would like to know what is the induced orientation on the rest of these faces versus what is the orientations I'm storing. So the blue is going to be the stored orientations, as in the orientations I've listed here. So first 1, then 2, then 3. However, on this edge, it is first 2, then 1, first 2, then 3, and first 1, then 3. Those are the orientations on the edges as they've come. But if you look at the induced orientations, the orientations that are kind of inherent in this simplex, they kind of go the other way. The induced orientations, they may or may not agree. So this particular induced red orientation is induced by this blue orientation on the 2 simplex. And if you take a look at that, you might say, all right, these orientations, do they agree? No. Let me give them a score of -1. Do these agree? Yes. Let me score them with +1. No. Let me score them with -1. To make this rigorous and systematic, the way we can do this is take a look at what's called an index, an orientation index. And the way that this works is it says if I have 2 simplices that differ by dimension 1, either 2 things happen. Either the smaller dimensional simplex is a face of the larger dimensional simplex, or it's not. If it's not a face, we'll assign the orientation index 0, as in it's not a face. On the other hand, if it is a face, they differ by exactly 1 vertex. If I have a 2-dimensional simplex that has 3 vertices in it, every one of its faces arise by deleting one of these vertices. Every one of these edges here arise by deleting one of these faces, but they might be in a different order. So the question then is, if I delete one of these faces, here, say delete this face, I get 2, 3. There it is. If I delete this face, I get 1, 3, 1, 3. If I delete this face here, I get something else. I get 1, 2. Now, the way to track this down is to say if I check the orientation, I'm asking if I've got some kind of parity check on it. If I have to have an even number of permutations to write this down as one of the other simplices floating around. So the right way to do that is to use this formal definition. And what it captures then is these signs.
Wouldn't 1, 3 then be a positive one?
1, 3, did I do this wrong?
Is it modulo or is it?
Yeah, there is some modulo-ness going on here. I guess 1, 3 would be +1, right? And there's an additional alternating sum as well an alternating sign thing that comes into here as well. Yeah, I think this should be like n + 1 or something like that. That's probably what it is.
That's why the stuff is so nasty.
Yeah, this orientation is nasty. I agree. Okay. Now, the point being, so long as you're consistent about how you end up doing these computations, in the end, it doesn't matter, which is saving grace. And actually, to be perfectly honest, when mathematicians usually teach this stuff, mathematicians are quite bad at signs. We end up saying, well, you know what? I'm not actually going to do this with real arithmetic. I will do this with binary arithmetic. There are no signs. I won't do that. We'll keep the signs. OK. So all right, now I can build your chain complex. So remember I said the first thing that we should do in our chain complex is the dimension of each of the vector spaces in the chain complex should be what? It should be the number of different simplices. So if I have the kth vector space, that should be the number of k simplices. So that's exactly what I've got here. I've got a space ck. It's a vector space whose basis is the set of k simplices, abstractly, in this categorification way that we talked about in the previous lecture. So as a result, the dimension of ck is equal to the cardinality of the set of k simplices. Great, OK. So that, right on the face of it, takes care of the fact that we're going to link up the chain complex, the alternating sum of those dimensions, is going to be exactly that Euler characteristic. So we've got that taken care of. Now, on the other hand, we want this to be a chain complex so that we can compute the homology. So how are we going to do that? Well, we need to build up some linear maps that go from one space to the next. Now, we do have a little bit of flexibility here. We can go up or down in dimension. I could build my chain complex so that I go from dimension k to k + 1, or from k to k - 1. I have an option in how I build that. And what I'd like to do in either case is I'd like to establish that what these maps are doing is they're telling me how the attachments work from dimension k to k + 1 or k to k - 1. So I want to encode those attachments, and I'd like to keep track of this orientation as well. And the way to do that is, if you're coming up with homology, what you will do is you go down in dimension. So I say, if I've got an edge, what are the vertices that it's hooked up to? If I've got a 2-simplex, what are the edges that it is hooked up to? And how do I do that? Well, what I do is I say, well, let me define a linear map on basis elements, and then extend. So let me take a basis element B, which is a k-simplex. So it's a list of k plus 1 vertices. Now, I'd like to know, what is the boundary of this? Well, if an abstract simplicial complex, I can find the boundary of this thing, find all of the boundary faces, the k minus 1 faces that exist of this thing, the k plus 1 faces of dimension k minus 1. How do I do that? By deleting each successive entry one at a time. That will give me all of the faces. And then I can throw in the orientation index. And here we go. Here is one way to do that. So what this is doing is this is taking each and every face and computing the boundary. So let's go back to this example and see what this map looks like. This map, let's take a look at this map boundary 2, which will go from C2 of my space to C1. So going from 2-dimensional simplices to 1-dimensional simplices. There is, of course, a map from C1 to Z0, which we can talk about as well. But C2, how many 2-dimensional simplices are there? Just one. So this is a 1-dimensional vector space. So this is R1. And how many 1-dimensional simplices are there? There's 3. So this is R3. So this is a 3 by 1 matrix. And what does that 3 by 1 matrix do? Well, here is my 2-dimensional simplex as the basis element, 1, 2, 3. And then I've got the various other basis elements. This is, say, 1, 2, 2, 3. Actually, let me capture exactly what I've got there. 2, 1, 2, 3, and 1, 3. 2, 3, and 1, 3. And then you just read off the orientations. So this is a -1, a +1, and a -1. So I'm just reading off these orientations into this matrix. So this is exactly what boundary 2 is. Now what about boundary 1? Boundary 1 goes from C1 to C0. We already know this is R3. This is, how many vertices do I have? 3. What this matrix is going to tell me is this matrix is going to link up. It's going to link up the vertices with the edges. So let me list out the vertices. There's vertex 1, vertex 2, and vertex 3. And the same ordering here. I've got 2, 1, 2, 3, and 1, 3. And I'm going to be making use of the orientations as listed. So which are the orientations as listed? Let's just use this formula as written here. So the 2, 1 edge, 2, 1, if I delete the first entry, what do I get? Delete the first entry, I get 1. And I read it with n is 0, so I get just a +1. And here I get a -1. And here I get a 0 because there's no 3's there. What about this one? I delete the first entry, I get a 3. It comes in with a +1. Delete the second entry, get a 2 with a -1, 0. Here I delete the first entry, I get a 3 with a +1, a 0 here, and a -1, 2. So those are the two matrices, boundary matrices. Now what about boundary 3? Well, it goes from C3 to C2. Both of those are 0-dimensional because I don't have any 0-dimensional to 1-dimensional. So boundary 3 going from C3 to C2, this is a 0-dimensional space then to a 1-dimensional space. So it's a 0 by something matrix. It's a 0 matrix. And all the other higher ones are 0 as well. OK, so this construction here is a chain complex. It's not obvious that it's a chain complex. And these signs, these orientations matter. So what you can do is you can start writing this down and checking it. So let's actually walk through why this happens. So if I take the successive 2 maps, one after the other, So boundary k and boundary k minus 1 go down 2 dimensions. If this thing is going to be a chain complex, this thing better be 0. So let's see if that works. So, well, I'm going to write down the definition. Right from the definition, if I take A to be a basis element of ck minus 1, then just grabbing the formula from the previous slide, there it is. Okay, that's just substitution by definition. Okay, now this is a linear map, right? So I should be able to pull out the sum and rearrange things a little bit. So that's just linearity. Now what I should do next is I should drop in the definition of boundary k minus 1. I'm going to now parameterize over another basis element, that of ck minus 2. Again, well, this is a linear map, so I should use linearity. Now, at this point here, what I've got going on is I've got a basis element of ck minus 2. So that's the range of this composition map. And I've got this thing here. This thing is a big coefficient. So a whole bunch of zeros, plus 1s, or minus 1s multiplied together and added up. So what could that thing be? Well, let's look at it. Let's look at what it is. Essentially what it is it's the index that comes about from deleting first this guy, then this guy, or the other way around. Deleting 2 vertices out of this list. If I delete those 2 vertices, I could delete them first this one, then this way, or I could delete them in the opposite order. First this one, then this one. Those are really the only 2 ways that I could come up with that index. And as it turns out, that they come in with opposite signs. If they come in with opposite signs, then this sum here has exactly 2 non-zero terms. One is positive 1, one is negative 1. 1 minus 1 is 0. So in fact, this thing is a chain complex. OK. So what this means is this construction that we've put together is a chain complex. Now, what does that mean? That means that the homology, then, of this homology construction that we built it for the purpose of matching up the Euler characteristic from this sort of combinatorial counting thing so that it also comes from a chain complex, which means that there is a homology that's associated with it. This is a homological property. So that means we've turned topology, this combinatorial topology, we've turned it into a homological data. And in fact, this is what homology is. So first of all, what we've done is we have put together this chain complex in a way that seems pretty useful. It's computing Euler characteristics. Homology is now well-defined. What does it measure? Well, the dimension of these homology spaces now measures topological properties, those topological invariants that we wanted to compute from the outset, and I mentioned yesterday. So, for instance, the dimension of H0 is the number of connected components. Dimension of H1 is the number of undirected loops. Dimension of H2 is the number of essentially bubbles or voids or sort of the interior of a sphere, and so on up the dimensional chain. Pretty cool. Let me show you how this can turn out to be useful. So here's a particular kind of topological space, particular kind of abstract simplicial complex that's associated with wireless networks. So if I have an ad hoc wireless network where I have multiple nodes and they can communicate with one another, they have radios, they transmit signals, and if I have 2 nodes that each lie within the region that's lit up by the other, then they can communicate. So these 2 nodes here, this green node lights up a region here, and the red node can hear it, but the red node lights up a region that the green node cannot hear. So these guys are not connected. On the other hand, these guys are connected because they're areas of sufficient power, sufficient bit error rate, whatever you like, sufficient signal strength in some abstract setting, is such that they can communicate. So imagine how you have a wireless network with these various signal level functions, and you build a link complex. So you build a flag complex over that. We'll call it the link complex. We've seen this sort of thing before. In the previous day, we were building sheaves over this sort of thing. But now you can ask, what are some homological properties of this? Well, how many connected components does this thing have? This thing is going to have 2 connected components. This is something that says the dimension of H0 for this guy is 2. Dimension of H0 of this guy will be 1. This turns out to be kind of a valuable homological invariant. So in particular, if you look at the loops, the dimension of H1, it can discriminate between this kind of network, which is sort of a loopy network, as in there's a loop around here, versus this network, which is very heavily connected. Now, in essence, this is very much like a wired network, not a wireless network. Because, well, basically each of the links are pairwise and they really don't involve multiple nodes at any given time. This network, on the other hand, is manifestly a wireless network in that if I turn on one of these nodes, lots of other ones hear it. There's a lot of broadcasting going on here, where there's not so much broadcasting here. Turns out this property is actually very important. In simulation, you would realize and you would imagine that what would be the case is that if I have very little traffic, not a whole lot of traffic, this network is probably better in that if I want to pass traffic from one side of the network to the other, all I've got to do is just one big broadcast, and that gets the data from here to here. What happens over here, if I want to get the data from here to here, I have to do a lot of forwarding. So the latency isn't quite as good here. On the other hand, if there's a lot of traffic, awful lot of traffic, what ends up happening here is you end up having to wait because you have to wait your turn to transmit because other people are transmitting. Over here, you have the ability to let some traffic percolate through the network, and it runs a little bit faster. So that homological invariant is a good way to discriminate how your network's going to stand up in high traffic situations. This turns out to be a useful thing, and we're, in fact, experimentally, you can show that's really what's going on. OK. Now, homology that we've just computed, it is a functor, as in it is an appropriate type change kind of operator. And it plays along very nicely with abstract simplicial complexes, which is to say, if I have two abstract simplicial complexes and I map one to the other, map it one to the other, mapping simplices to simplices in a way that preserves attachments. If I preserve attachments, I'm preserving that topological structure. Well, if I do that, what happens? Well, on the level of each space in my chain complex, what happens? Well, I've taken simplices to simplices. So that's a nice linear map there. Another simplices to simplices, nice linear map there. I do that, and I preserve the attachments. The attachments now are instantiated as these linear maps. In some sense, they're a particular categorification with appropriate orientation coefficients of this map. So they come along for the ride. And so what I end up with is I end up with a morphism between homologies. That's pretty useful. That means homology, if I go ahead and map one space to another through a nice map, then in fact, I end up mapping the homologies as well. So the homologies can get transferred from one space to the other. So in particular, I can go ahead and think of homology as being a reflection of what's really happening on the level of the spaces. It's a summarization. Taken a topological space, an abstract simplicial complex, which is a fairly big combinatorial object, and turned it into a bunch of vector spaces, such that if I change the topological space, I change the vector spaces in an analogous way. It's a very powerful concept. Now, what can I do with this? Well, there's something kind of funny. See, it's one of my favorite pictures. You look at it, this can give you the ability to zoom in on different parts of a topological space. So H0 or H1 measure the number of connected components of the whole space, the number of loops of the whole space. If you've got a huge amount of data, the whole space is going to be too much to work with. You won't be able to fit that in memory. You won't be able to compute with it. On the other hand, what you would really like to do, in many cases, is you're interested in some part of that space, interested in some particular vicinity. It's kind of like if I'm interested in, say, 10th Avenue, I don't really care what the rest of the world looks like. And indeed, what you're doing is zooming in very much on a part of the space, working with that part of the space, and the rest of the space is still there. Still there. It's not gone, but it's sort of not entirely present. So the way this map, of course, goes, not to explain the joke to the point of painfulness, but this is a New Yorker's view of the world. Manhattan is in great high definition. And then there's like Jersey across the Hudson River, and then, well, there's some stuff, and then, Japan and Russia on the other side. This is actually a good analogy for what we're going to do topologically. We'll zoom in on a particular portion of the space, analyze how that particular portion of the space looks by zooming in. Now, we're not completely forgetting about the rest of the world. The rest of the world is there. It's just far away. It's like over there, across the Hudson somewhere. So let me show you how this works. So in order to do this, we need to take our homology and turn it into a computation that allows us to ignore in some fashion. This goes under the name of relative homology. So instead of using the chain complex that we had before, what we're going to do is we're going to throw out some of the basis elements. We're going to throw out some of the basis elements corresponding to k simplices we don't care about. So if I've got, remember, what is this? This is a vector space whose basis consists of all of the k simplices. This is the vector space whose basis consists of all the k simplices in the subcomplex A. So what we do in order to form this quotient is we list all of those k simplices and just throw away the basis elements corresponding to A, rather. So that's this quotient. This quotient is all of the vector space basis elements, all of the vector space built up of all of the k simplices that are not in A. Use the same boundary maps with a little bit of modification. All you need to do is delete the rows and columns that don't apply. Just get rid of them. That thing still is a chain complex. And there's a theorem that goes under the name of, of a quotienting theorem here. And what it does is it says, if this is what my space X looks like, and this is A, these two vertices, what you'll end up with is you'll end up with what looks like this space with these two guys collapsed down to a single point. Now, this single point sort of plays the role of the point at infinity. If perhaps the analogy of stereographic projection, I've got a picture of a sphere, map of the Earth, and I've taken it and unwrapped it, and around the edge of that map is, well, it's sort of far away from the middle of the map. That's, in fact, the role that A plays in this collapsed space. Now, important technical point, I say k greater than 0. In k equal to 0, something weird happens. In essence, you end up losing a dimension that you thought you would have had otherwise. And so sometimes people will call this reduced homology. For the purpose of what we tend to do, we tend to be interested more in first homology than in zeroth homology. Zeroth homology is clustering, finding connected components. We're interested in some of the higher dimensional topological features, so that turns out to be a better way to look at it. And just ignore the zeroth homology for the moment. Okay, so how does this work? Let me show you how this works in a specific case and how to turn this into this New Yorker's view of the world. So let's take a simplicial complex. This is a simplicial complex X. And let's zero in on one particular vertex. That one particular vertex, A, which in this particular case, let's say it's 4. Let's zoom in on this vertex 4. If we want to zoom in on it, we want to have a high definition view of everything in the immediate neighborhood. And we don't care about the rest. So what are we going to do? Well, first of all, we need to know what a neighborhood of that is. What's the neighborhood? Well, from the previous lectures, we said the neighborhood is a star. So let's take the star over 4. There it is. We want to keep that neighborhood. We want to see that in high definition. We want to see that whole neighborhood. On the other hand, we don't care about everything else. So what's the everything else? The everything else is the whole everything else minus the star. So that's this portion of the network. So get rid of what we're not interested in. So this portion here in bold is everything that is outside the star over 4. Now what I'm going to do is I'm going to form then that relative quotient construction where I'm going to take all of this stuff in bold and send it to the point at infinity. So now algebraically, it looks like this particular homology space, what it's doing is it's showing you a zoomed in version here around 4, but everything in bold, everything that's the rest of the world has been collapsed. Yeah?
Do the edges and the face also go to that?
Yep, they sure do. They all get collapsed down. Yep, they all get collapsed down. So in essence, what you see is you see these things here kind of pinch off. These pinch off.
But those two faces remain.
The two faces remain. The two faces remain. Yes?
They remain as two faces?
They remain, well, this is not a topological space that we're looking at. This is an algebraic construction.
Right.
So this is purely in the level of algebraic constructions. That's actually what this theorem says, is that you can look in the Alexandrov topology to figure that out. It's not necessarily the right thing to do, actually. The right thing to do is to think of this purely as algebraic. And what's interesting about this is let's take a look at what some of the invariants are present. Turns out for different k, you see different things. When k is equal to 1, this is a generalization of the degree of graph. So in particular, if I take a look at h upper 1 of a graph, say x is a graph, it's a one-dimensional simplicial complex, and I do this local homology, as it's called, compute it at a vertex, I will recover the degree. This is the degree. How does that work? Well, here's the picture. The picture is actually very, very clean. Essentially what it says I take my vertex. Remember what I'm doing? I'm taking the star, deleting the neighborhood, or deleting everything but the neighborhood of the star. So here's a vertex in my graph, and there's other stuff out here. I don't know what the rest of this graph is, but there it is. So I'm going to zoom in on this vertex. So what am I going to do? Well, first of all, I'm going to take the star. The star is there. That's the star. And I'm going to get rid of everything that is not in the star. So everything that I'm getting rid of is in red. In essence, what I'm doing is building up the following picture. But now each of these guys here are all glued to the point at infinity. And you ask, how many loops are here? How many loops are here? Yeah, there are one. Okay, that's a good question. These are all the same point. So let's draw it that way. That's right. So let's say there is that black vertex and the point at infinity. I've got one edge. This is really what I've got. I've got this black vertex edge, vertex edge, vertex edge. Each of these guys go off to the point of infinity and come down. So how many loops do I have here? Well, if I'm looking at this from a counting standpoint and an algebraic standpoint, what I probably will end up with is I'll end up with one loop here, one loop here. And what about this other loop, the big one? The big one here seems to be there as well, right? But the big one, as it turns out, I can form this big one by adding these two loops. If I take this loop here and imagine traveling out this way and then whoop, following the next one right around, grab that point and sort of stretch it back up so that I end up just traveling this loop. So this loop is actually kind of redundant in some sense. So the number of loops that I have present here is actually 2. I can compute that homology for you as well. So you can see that the dimension of this homology is 2. So how does that work? So I've got, this is boundary 1. And how many vertices do I have? I have 2 vertices, and I have how many edges? 3. Let me call this edge 1, edge 2, edge 3. This is edge 2, and this is edge 3. This is vertex 1, and this is vertex 2. This is not an abstract simplicial complex. The construction still works. And wait, I got this going the wrong way. I'm transposed. It's supposed to go from edges to vertices. There we go. All right, edges to vertices. So the space of edges, this is going from C1 to C0. So let's see here. I've got this first edge has vertex 1 and vertex 2. The second edge is vertex 1, vertex 2, vertex 1, and vertex 2. Could have chosen the orientations a different way. What is the rank of this matrix? Yeah. Which means the kernel of this matrix is what? How many dimensions? 1 or 2, right? It's 3-dimensional matrix, a 3-dimensional input. Rank is 1, so the kernel is 2. Right. Now, what about C2? What's C2 in this space? 0. There are no two-dimensional faces. So going from C2 to C1, this is actually a 0-dimensional space, and this is an R3. So boundary 2, the image of boundary 2, image, AG, the image, this is 0. So this is the, this is the dimension of the kernel. Sorry, this is the dimension of the image. So H1 is dimension of kernel, of the kernel of boundary 1 modulo the image of boundary 2. So the dimension of H upper 1 in this, H lower 1, dimension of H1 is 2. So it turns out, I think I've got actually a typo on this slide. This should actually say degree of V plus 1. This should say degree of V plus 1. Minus 1, minus 1, minus 1. Plus 1's on the other side. Yeah, degree of V minus 1. So the degree is 3, and we've got the 2 loops there. This is a very useful construction because graph degree doesn't make a whole heck of a lot of sense here. What's the degree of this vertex? 4. This is 4. But the fact that I've got these pieces glued in here really means that this has got one input over here and one input over there, so to speak. This really feels like it ought to be a degree 2 kind of vertex. But it isn't degree 2, it's degree 4. But this local homology really captures that in a nice way. So the H lower 1 is a generalization of graph degree. As I said, off by 1. I'll correct that slide. OK. Now, the other thing that's neat about this is that if you're not at a vertex, an interesting vertex, it measures dimension. So in fact, this is a way to homologically measure dimension for dimension reduction. So if you're sitting in the middle of a space that looks very much like a manifold, we can compute the dimension of this by asking for what is the highest dimension. If this thing looks like all zeros, and then the very last point it's 1 and then all more zeros, that where it turned to a 1 just briefly, that's the dimension. It looks like a dimension of a manifold there. And the idea here is that what it's doing is it's measuring if your space looks very much like the surface of a sphere. That's what this is computing, because essentially what this is the homology model of a sphere. It's called a space that looks like this is called a homology sphere. So what this is doing for you is this is able to allow you to tell the intrinsic dimension of your space. So if I've got some complicated space as an abstract simplicial complex, I don't know what it is. If you do this computation and find something that looks like it's all zeros and then 1, and then the rest all zeros, then you know the thing looks very much like a manifold at that particular point. So if you're in the interior of an edge, you'll see this as well. Why? Because I take the edge and I collapse everything out. So I fold it together, and it looks like a single loop. Now, there is something a little problematic, is that this particular invariant isn't necessarily robust to noise. We'll fix that in lecture 8 when we talk about persistence, because you can compute these local homology invariants via a persistence approach that makes it a bit more robust. And sort of the parting comment here is local homology actually is a sheaf. That if I take a look at zooming in on a particular spot by way of moving to smaller sets in my Alexandrov topology, this local homology ends up being, because homology is a functor, it ends up still coming along for the ride. So if I start with a K simplex A that's a subset of a larger simplex B, then just taking a look at it, the stars are also the same way. The complements go the other way. And that ends up inducing, through a little bit of algebra, inducing a linear map, because homology is a functor. So in particular, this thing is a sheaf. Pretty cool. And local homology is, in fact, a sheaf that every space comes with, or at least every simplicial complex space comes with, that you can study and make use of. And in particular, it's one of the ones that, if you don't have any other data, it's a very valuable one to play. So next up, you can see lunch is being prepared, and we'll talk about sheaf cohomology, which takes these ideas and then completes the circle, lifting them into sheaves. And there are some references, so thank you.